have a non-homogeneous term. So what we will do, we will apply, and also this initial condition is 0, or you can say that some constant initial condition, but it is not a variable initial condition. It is not like a function of x. That is the main thing which we need to apply the Duhamel's principle. When you have a heat equation with a source term, when you have a heat equation with a source term, and also the initial condition is a constant initial condition, then we apply the transformation of the variable u, like we will apply some kind of transformation. U will be transformed to u tilde such that this heat equation will reduce to a homogeneous heat equation. So u tilde t is equals to Laplacian of u tilde. And in that case, when we apply this transformation u to u tilde, the problem, the non-homogeneous problem will reduce to the homogeneous problem, and consequently your initial data now will not be a constant initial data, rather than it will be a variable initial data. So this is the main property of the Duhamel's principle. This is the same thing which I have written in this here. A general method for solving a non-homogeneous problems of general linear evolution equation. So this is general linear evolution equation. U is evolving over time, and also U is evolving over the space variable. Using the solution of homogeneous equation with variable initial data is known as Duhamel's principle. So let's solve. Given s is greater than 0, we solve the following homogeneous problem. And the initial data is now f of x comma s for x belongs to R8. Say this is equation number 3rd. Say this is equation number 1st, equation number 2. So what we are doing, we are taking a transformation from u to u tilde such that this f comes to the initial condition. So when this f comes to the initial condition, it gives the value of the function at some time s, and we don't have like s equals to 0. It may be a variable. So this reduces to the homogeneous problem, but at the same time now your initial data is no more initial data. It is a variable data, you can say. It is no more initial, it is a variable data. To obtain a solution, u tilde x comma t equals to capital U x comma t. So yes. Now we are getting a solution for some s greater than 0. So we are assuming that u tilde will be depending on s. However, you will use this u tilde to find out the solution of this problem. Then this s will be vanished. And how we are going to proceed? So we are going to see that procedure. Indicating the dependence on s is greater than 0 by letting u tilde x comma t is equals to v of x comma t minus s for a function v on Rn cross 0 comma infinity. Then we solves the heat equation with initial data v of x comma 0 is equals to f x comma s. Now we use the heat kernel to have such a solution as. Now, if you remember that when we have a homogeneous heat problem with a non-homogeneous boundary condition, then we can express the solution of that heat equation in the terms of the heat kernel. In such problem, we derive the heat kernel. But if we are unable to derive the heat kernel for a particular problem, but still we know that the heat kernel is a normalized function over the range. Heat kernel is a normalized function, like integration over Rn k is going to be 1. That we know. So we can write the solution as Rn k xy, and the solution of the homogeneous heat problem with the non-constant initial data. That non-constant initial data is supported by the heat kernel. In the same way, if you remember in the Poisson equation, Laplacian of u equals to f or Laplacian of u equals to 0, that was the Laplace equation. When we write the solution of this Laplacian equation, we calculated the solution in this form, where p x comma y was the Poisson kernel and the value at the boundary x comma a, like something, that was something phi. So it was the boundary value were supported by this Poisson kernel. In the same way, we have seen in the last class that the solution of the homogeneous heat problem is given in the form of this, where f is initial data, f is variable initial data, which is supported by the heat kernel. Is it clear to everyone or not? Is it clear? Like this? Clear? Okay.
Can you repeat that last part?
Yeah, sure. So this was the Laplace equation, and when we derive the Laplace equation either on the interior of a circle or the exterior of a circle, even in the rectangle, like the boundary, you know a fixed boundary, because if the boundary is unbounded, so you will not be able to apply the boundary condition. So you should have at least the interior boundary or exterior boundary, but that should be a bounded boundary. In that case, we derive the solution. Suppose this is uxx plus uyy equals to 0. This is a two-dimensional Laplace equation. So in that case, we derive the solution of the Laplace equation like integration from 0 to like r square p x comma y, and suppose it has some non-constant boundary condition u of x comma a equals to phi. So we write the solution in this form, phi of y equals to dy. Do you remember this? It means the boundary condition, the boundary function was supported by this Poisson kernel. Like this was the definition, that the boundary function is supported by the Poisson kernel for the Laplace equation. And in the same form, when it was Poisson equation, then the boundary function was supported by the Green function. We have already seen in the previous classes. Do you remember these things? And now in the last class, like yesterday class, we saw that when we have heat equation ut of uxx plus, don't write it as uxx, simply write it ut is equals to Laplacian of u. And this is a homogeneous heat equation because there is no source term, f is 0. So this is a homogeneous heat equation, and we have the initial data. Suppose Laplacian equals to del over del x1 del 2 over del x1 square del 2 over del x2 square dot dot dot. So x equals to x1 comma dot 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 xn. Suppose that u x comma 0 is given by a variable function u, that the initial data is given by some variable function. In that case, we could see that the solution of this equation can be written as u x comma t equals to integration k x y t f y dy. It means that the initial function was supported by this heat kernel, where the integration of the heat kernel was 1. Is it clear? So the same thing I am saying. If you have any doubt in this line, in these 3 lines, then you can ask. Okay. So in the same way, we are saying that if we are assuming that u tilde x comma t equals to v x comma t minus s. So at t equals to s, it is going to be, see, u tilde x comma s will be v of x comma s minus s. That is v of x comma, and u tilde x comma s is defined as f x comma s. So this is f. This is just a way to write it. Like we are assuming that v is a function, and we are defining v function in such a way that at t equals to 0, it is giving this f x comma s. Then Duhamel's principle asserts that the function u of x comma t is equals to integration 0 to t u of x ds ds x belongs to Rn. Now I am saying that this capital U that was equals to u tilde of x comma t is going to be solution of this equation, that is the homogeneous heat equation with the variable boundary condition. Then its integration over 0 to t is going to be solution of the original equation. How this is coming? Let's see the proof of this equation. Then the function this would be a solution to the original non-homogeneous problem. Formally, if you take it u x comma 0, so integration from 0 to 0. And what will be the value of this integration? The integration from 0 to 0, what will be the value of this integration? 0. Formally, ux comma 0 equals to 0, and when we will take the derivative of this, that ut and then uxx, then it is going to satisfy this equation ut minus Laplacian of u equals to f. Let's see. What happened, Ivan? Is it okay? Everything is okay to you? Are you sleeping?
I haven't slept like at all, so.
Yeah, I could see that you are sleeping, so it's fine.
Oh, but well, I think I'm alright. Maybe this is a dream, but yeah.
Okay, so when we are going to take the derivative, if uxt, that is the integration from 0 to tu. So basically, what is this integration? It is basically integration from 0 to u tilde of d of s. Then we are saying that the integration of u tilde is going to be the solution of the original heat equation, like the non-homogeneous heat equation. So what it should satisfy? It should satisfy the derivative of u with respect to t and the difference of the derivative of u with respect to t minus Laplacian of u should be equals to x. So let's see whether it is satisfying or not, because it is giving us the initial data. Initial data is satisfied. We are getting a constant initial data, isn't it? So let's see u of t x comma t. When we will take the derivative with respect to t of this integration, then we are going to use the, which theorem we are going to use?
Fundamental theorem of calculus.
Exactly. So we will use the fundamental theorem of calculus. U t x comma t is equals to integration from 0 to t u t x t s ds, the derivative of the augmented function plus the derivative of the upper limit, that is 1, and the value of u at t. So u x comma t and t, and then minus the derivative of the lower limit. What will be the derivative of the lower limit? It is 0, so it will be 0 0, and what does else comes, it doesn't matter really. And what is the value of this? What is the value of this? U tilde x comma t is going to be u x comma t s. This, isn't it? When we will be replacing t, just you need to focus a very small thing. I am using the functional analysis, but it is very basic functional analysis, so this derivation is very easy. You don't need to worry about. If we replace s to t, so what it will be? U tilde of x comma t is equals to f of x comma t, isn't it? And simply you can write u of x comma t, isn't it? So what will be this? F of x comma t. Is it okay? So u of t x comma t is equals to, this is f of x comma t plus integration 0 to t and what is the value of this? This u tilde x comma t was capital U x comma t and s, isn't it? And we have the information that u tilde is the solution of the homogeneous heat equation, isn't it? So u tilde t is equals to Laplacian of u tilde. So can we say that u capital U of t is Laplacian of capital U? Because both are same. So can we replace with the Laplacian? I haven't mentioned all the small things in your notes, but it is very trivial, so that's why I didn't mention. If I am saying that u of x comma t is this, and this is the derivative with respect to time. This is the derivative with respect to time. So can we say that Laplacian of u, this is the space derivative. So the derivative can be passed inside this integration. I need to take your test a lot today. So this is u x comma t is equals to capital U x t comma s is t. This is the integration with respect to time. This is the integration with respect to time. So what will be the first derivative of x with respect to x? Again fundamental theorem of calculus, 0 to t u x x t s ds, isn't it? Because t is independent of x, so the derivative of the upper limit and the derivative of the lower limit with respect to x is going to be 0. So similarly, if you take the double derivative, that is the Laplacian of u, so can we write this capital U? Is it okay? And we are using the same thing here. We are keeping the value of this is equals to it means this assertion which we were taking, this assertion is correct, isn't it? It is giving us the initial data and it is also satisfying the heat problem with the non-homogeneous term. Is not so if we have a non-homogeneous heat equation with a constant boundary, constant initial condition, then we can express that non-homogeneous heat equation in the terms of the homogeneous heat equation with the variable initial condition, with the variable initial condition, or you can say that variable condition. And we can write the solution of the given heat equation as the integration of the solution of this. So with respect to t. Is it okay? The derivation is fine, Roberto? Okay. This is the Duhamel principle, and I would like to ask you, please read it very carefully. It is the easiest topic, and in my point of view, I think if you are going to face these kind of questions in your interview, because this is very common question. So when you express the non-homogeneous heat equation in the homogeneous heat equation, then you know that the integration of the homogeneous heat equation solution, the integration of the solution of the homogeneous heat equation is going to be the solution of the non-homogeneous heat equation. And how you are proving, so you know the proof. You have to use the fundamental theorem of calculus and the proof is very easy. In our notes, I am mentioning that however we have to justify the differentiation under the integration. So for the differentiation under the integration, I am writing. Just give me a minute, and I am coming, and then I can show you the next thing. So the differentiation under the integration is valid or not. We are going to see with the continuity of the equation, with the continuity of the functions. Just give me 3 minutes. Yeah, we can continue. Now we have to justify the differentiation under the integration. So we are just doing some calculation. And you guys are very much aware of those calculations, so it is not a big issue for you. So, okay, so you already know the solution. Can you please tell me how we can write the solution U in the term of the heat kernel? You know the heat kernel. Now you have everything.
Well, it will be like the integral
Mm-hmm.
from
Mm-hmm.
Rn,
Mm-hmm.
and you have like the, the kernel, the heat kernel,
Mm-hmm.
and it's multiplied by a function, right?
Yeah.
The
This was
initial conditions.
this was the solution of the homogeneous heat equation, isn't it? So this will be the solution of this equation. However, to write the solution of this equation, we have to take again the integration over 0 to t, isn't it? Is it clear, Roberto? If you have doubt, then please ask, don't feel shy. So, this is the heat kernel and this is the variable initial condition for the homogeneous heat equation. This is the variable initial condition for the homogeneous heat equation, isn't it? Now we know the value of the heat kernel. For n dimension, we know the form of the heat kernel. So it would be 0 to T 1 over 4 pi T minus S whole to the power n over t integration over Rn. So this is the constant which is basically to normalize the heat kernel, and e to the power mod of x minus y square over 4t t minus s, because we are writing here t minus s, and this is negative f s f y comma s dy over ds. This constant will not go outside of this integral, because again we are applying another integral with respect to t. So this is just a way. I can also write it like this. Just let me write it. This constant can be written outside of this integral, because this is integration with respect to the space variable. So whatever the way you are right, just this constant cannot go outside of the time integration. And can you see that if we have a non-homogeneous heat equation with constant initial data, in that case the solution can be written using the Duhamel's principle, and the solution will be like double derivative, double integration, one integration with respect to time and the other integration with respect to the space variable. So this is the beauty of the Duhamel's principle. X is belonging to Rn and t is greater than 0. So this is equation number 4. In this when someone asks you in the exam to use the Duhamel principle, like I have written in the notes, just this derivative and this derivative, you need to explain all the derivative, how we are passing the derivative inside the integration. So you have to mention the fundamental theorem of calculus, and then you have to write the derivative of the upper limit and then minus the derivative of the lower limit. Okay? Like this is understood for me. Here I explain, so you have to keep it in your mind when you are solving a non-homogeneous condition. So in the following, we use C1 square omega cross I to denote the space of functions uxt on omega cross I such that u t u u t u x I u x I x j are in C. So if we are saying that u is a solution of the heat equation, then the second order derivative of the u should exist and it should be continuous, isn't it? The second derivative. So this is the way. In the following, we use C1 square omega, that is domain, cross I, that is time, to denote the space of function u x comma t. So x is coming from the domain omega. Omega is contained in Rn, and I is the time interval. So t is coming from that time integral, and time integral is taken to be a delta cross infinity. So when you talk about the solution of the heat equation, you say that the solution, that is the space of function u, that is basically the solution. The space of function u is coming from this space, because we know that if u is a solution of the heat equation, then its first order derivative with respect to time, first order derivative with respect to space, second order derivative with respect to space variable should exist, and it should be continuous to be a smooth solution of the system, isn't it? Is it clear? So here I took the time, the interval for time I, that is delta comma infinity. Now on the basis of this analysis, I am going to write another theorem, that is known as Tychonoff theorem. No, this is another theorem, and after that we will be going to the Tychonoff solutions. So just have a look at the theorem. Assume that f belongs to the function of the second order continuous function on Rn cross 0 comma infinity. So the non-homogeneous function is second order continuous on the whole domain, is such that f, its derivative with respect to t, its derivative with respect to xi, and its double derivative with respect to space variable are bounded on Rn cross 0 comma infinity. Now define uxt by 4, then u is belonging to C1 to Rn cross 0 comma infinity, and satisfies ut x comma t. Shall I give the proof of this theorem? I think it will be easier to all of you to see the proof, because it is similar what I have explained by the solution of the non-homogeneous heat equation. The proof is same. So if you want, then I can write the proof, like I can explain. But do you want I have written the proof in your notes, but if you want, then I can explain.
Um, but uh, but I don't know what satisfies.
The step is that here we are saying that the space function uxt will be coming from c1 square omega cross I, where I is the integral delta comma infinity. Delta is some positive, small positive number. Now I am going to expand this interval I from closed interval 0 comma infinity, and we will say that the space function u will be coming from omega cross closed interval 0 comma infinity. So this is the proof, and the proof has been like this is the extension of the solution which I gave you. So it has been proved in the same way like we solve it. So do you wanna know the explanation from my side, or you will be doing it alone?
Um, I think, well, for me, it's okay if
This
we
thing,
continue.
yeah, this thing was clear to all of you.
Mhm.
So don't worry about that theorem. This will be very easy, and please read that theorem today so that in the tomorrow class, if you don't get it, we can discuss. Don't left any of the theorem or the exercise of this unit, because this unit is proceeding very fast. Today I'm going to write the Tikhonov solutions and the non-uniqueness of the heat equation. Then we will be coming to the maximum minimum principle, and let me open the syllabus. I think by the next week I will be completing this unit. So we have the fundamental solution of the heat equation, that is the Poisson kernel I have written, but it was heat kernel. Problem with initial and boundary value, that's done. Tomorrow I am going to complete weak maximum principle, that will be done. Duhamel's principle have been done. Today I am going to discuss the non-uniqueness, so that is, now we will be left with Wider's theorem and the principle of maximum in strength and uniqueness and its application. So the next week will be the end of the heat equation. I think this unit was really very easy, isn't it? Like there is no topic which is difficult. Is there any topic which is difficult to deal with?
The first one,
Elliptic equation?
like the shock wave and the Monge clones and all that,
I
that was
would
pretty
like to
difficult
ask
for
you
me.
one thing. Do you guys need another class explaining the shock wave and the Riemann problem and the real fraction wave? Do you need?
Can we, like, at the end, make like a summary of all the course, like just like in a very broad way,
Can be made?
like a summary or a review of like all of the subjects, like in a very broad way.
All of the subject I cannot say. I can talk about the my.
Oh, yeah, that's a lot, right?
Yeah. So
Yes,
I would like to.
that's a lot.
Yeah, I would like to give the explanation of the unit second again. And but before that, I would ask to Yvonne, please write me all the topic which you have confusion, in which you have confusion, like the shock wave. Please read and write to me. Then I will take,
Okay.
because unit two, I believe that unit two is the easiest topic for me, easiest,
Mhm.
and I want that unit should be easiest for you as well, because that is my research area. So I have a very strong command on the unit 2, and I want that you should be very good in the unit 2 if you are taking my class. I tried my best. I think Camilo has a lot of clear concept of unit 2, isn't it? Camilo has a lot of clear concept, but Yvonne, you will write me an email and write me all the topic which you are feeling like facing the difficulties, and then the next week I can schedule an extra class to complete those topics, and with all the doubts you want, you can ask to me. If it is silly, it doesn't matter at all. So we can discuss. And the elliptic has a lot of theory, so I cannot say it is mixed. Elliptic equations has mixed theory, but the heat equation is really very easy. We are just using the fundamental theorem of calculus and some basic theory of functional analysis. Yeah. So the heat equation is going to be the easiest one if you are aware of the elliptic equation. So firstly, you have to complete the elliptic equation, then you will come to the heat equation, then it will be easier. And don't worry about the unit 2. We can again go over the unit 2 and yeah, we can again go over the unit 2 and we can complete it. Well, I have this library by Mexico City. I really love it. The that building, the library building, and its infrastructure. I really love it. Have you visited to Mexico City, Camilo? So I will be going and I am gonna take pictures there. I was just like I love it. It was the first time when I came to the UNAM. So I was thinking that I am going to be there. He is sitting in the biblioteca. Yeah, so that building is really very nice.
Yeah, I think it's like you are referring to the like central campus library, the like the big library, or the math library.
I am talking about the main library, which building? The building was painted by a famous painter.
Yes.
So I will be visiting, like I will be visiting Mexico City campus in November. I'm gonna explore all the buildings like that building, and there is a place um, that has that is the administrative building. I'm gonna visit that building. So I just wanted to explore the next. Unam is the seventh most beautiful campus in all over the world.
Yeah.
So I will get an opportunity to visit Pune this month. So the non-uniqueness of the. So you are not sitting in the main library.
We should like schedule like I don't know, like invite you to like a colloquium here or something. It
I
could be
know.
like fun, or just like
I am just
oh you.
with my friend, one of my friend,
Mm.
and she is doing PhD. Yeah, she is doing PhD. So I'm just gonna visit there for to visit the campus. It is not colloquium.
Yeah. Okay. It's like more like you just want to know the place. Todos los demás siguen aquí.
Yeah, I think the network automatically went, and I think that's why Kamiko left. Yeah, now he's there.
Ah, okay.
Yeah,
Están en el.
it was an issue with the Unam network. It automatically went down, like it went down, and I was thinking, what happens to me?
Camilo, deberías de venir con Sarvati también para acá.
Sorry.
Ah, I was saying that Camilo should travel here in June to like know each other in 4 dimensions.
Ah, yeah. Come, have you been in Mexico City, Camilo?
Sorry?
Have you been? Ah, so he was appearing in 4 dimensions.
No, 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 no. Well, like in person, you know.
Ah,
Uh,
yeah.
I think Camilo, you have come to Mexico City, right? To turn in the papers for the inscription. So
Mm-hmm.
uh, you haven't met like all of the buildings here in Mexico City. You haven't been in Mexico City.
I haven't been in Mexico City campus. Just I have been in Mexico City more than 7 times, but all the time I have been in Polanco or somewhere another good places. I haven't seen the Chapultepec and a lot of things. But my motive is first to visit the Mexico City campus. But I am thinking to visit uh, Museo de Arqueología y
Hmm.
Palacio de Herrera. No, what you call it?
Palacio de Bellas Artes.
See, y Chapultepec. Yeah. So
Yeah.
this is in the my list.
Yes. There are they are must visit
Yeah,
places.
so the Museo de Arqueología and Palacio is my first, like, I want to first complete that, and then in the second, I would like visiting Tuna just to explore the campus.
You can like take a bike and then explore everything like faster.
I am coming via car, and I am going to explore the campus with car, so I don't need to worry about.
Oh, okay. Well, yeah.
So one of my friends, she has her car, so she is visiting, and she is doing PhD in this campus, and she is going to Mexico City campus. I'm gonna join her.
Initial.
So the Cauchy problem
Initial.
defined by this and with the variable initial data, So there is a theorem that talks about the non-uniqueness of the heat equation, So there might be more than one solution of the homogeneous heat equation with the variable initial data. And
Datum.
the theorem which proved
Datum.
that it has more than
Datum.
one solution
Datum.
is known as that kind of solution is
Datum.
known as Tychonoff solution. So he or she, I don't know. So this is the author who gives the infinite solution of the homogeneous heat equation with the variable initial data. How he constructed that solution. So we are going to see that how he constructed that solution. So this is also one of the topic, like it haven't mentioned the name in your syllabus, but it is also coming from your syllabus. It is an important topic.
Is there a theorem that assures you like if if a a differential equation doesn't have unique solution, then it has infinitely many, or it can have finitely many solutions.
It is infinitely many.
Yeah, it's just one or infinite, right?
Not on infinite, yeah, because when we talk about the finitely many, so there is a theorem which comes in the linear algebra. I don't remember exactly. Either it have infinite solution or it have single solution. The finite case does not come here for the heat equation, because we are going to prove that the solution will be like, there will be a variable theta. Theta will change the solution. It will also be the solution, and theta is coming from R. So it is infinite, and in fact, you can say that I am just checking. It is uncountable, in fact, because like there is a function theta, and theta is function of alpha. Alpha is greater than one. Alpha is greater than one. It means alpha is belonging to open 1 comma infinity, and this is a real number, so it is uncountable, so it is going to have uncountable solution, not countable. If it was coming from z or natural number, so it was going to be countable, but since it is coming from the interval, so it is going to be uncountable. Camilo, do you understand the concept of countable and uncountable sets?
No, but I can read that.
uh, you need to study about the countable set and uncountable set. So the number of points in the countable set is like it can be equivalent to the countable set, and but the number of point in the uncountable set is going to be like there is a term. What terms it calls?
Aleph,
Alpha
Aleph, Aleph, Aleph.
in English.
I don't know. It's like an N with zero and yeah.
Yeah, that's but this is zero and n, yeah, but it has a name.
Uh, or ordinal numbers.
No, it is in my mind, but so you can go over that. It happens because R is union of the rational and irrational number. So irrational number is
Yes.
uncountable. So because of that, you need to go over that. And yeah, here I am going to construct a very special kind of solution. So you don't need to ask me a question because that solution was given by this author. He constructed that solution, and when we will be coming to that solution, that form of the solution, and you put it back in this equation, then it is going to satisfy this equation with the initial condition. So it is like you are trying some problem and you are able to find a solution when you change the variable, but still it is going to be solution. Even you have the initial data, even you have the given initial or boundary data. So this mathematician was able to do that. And how he did that? So let's have a look. We only need to construct infinitely many non-zero solutions to the one dimensional heat equation with zero Firstly, we are going to take a zero initial condition, and then we will construct the solution of that problem, and then we are going to pass to the original problem. We first solve with the zero initial condition. We first solve the following Cauchy problem ut is equals to uxx. X is belonging to R. T is going to be minus infinity to plus infinity, and u of 0 comma t is equals to zt u of x 0 comma t is equals to 0. So the author is being very clever. Rather than treating t as a time variable, because as soon as t will be the time variable, so every time you have to take t is greater than or equals to 0. What he is doing, he is taking t as a space variable, that is t is coming from minus infinity to plus infinity, and x is belonging to r, so just proceed with the one dimensional. And then he is also changing that condition, he is also changing that condition to 0 comma t, just reverse the role. So 0 comma t with z comma t and another initial condition, not initial, I won't say that it is the initial condition, rather than I would say that he is trying to convert the initial condition, initial value problem to the boundary value problem, ux 0 comma t. So which kind of boundary condition is it?
The first one is Dirichlet and the other is Neumann.
So this is a
Rowing condition.
Yeah. You really just don't need to mention that it is a Robbins boundary condition, rather than you say that this is just a way to proceed. Actually, I did not get the logic why the author is doing so. Still, I am reading this. This looks very interesting, and you can use this kind of step to solve a number of problems, like another problem which you use in your real life simulation, like reaction diffusion equation and the Schrodinger equation. So I am going to work on this. I found it in a research like in a paper, and I really like it. But still, I cannot go over in the deep of this way. Why the author is proceeding in this way? Why? Right now, we first solve the following Cauchy problem. Do you know that sometimes the solution of a given problem can be expressed as the summation of the Taylor series? It takes like we write the solution of some PD as the power series, isn't it? This is just a way to solve. But power series method has some drawbacks. So there are three very useful method to solve a PDE of one dimension. One dimension with time variable, so t and x. So this is going to be form a PDE, isn't it? So the first author uses that the power series, and then there is also that is known as just let me find out. This is also very interesting problem.
With M, the only thing it comes to mind is like Maclaurin series.
No. Homotopy analysis method. Homotopy analysis method is a very powerful technique to solve a PDE. So what does it does? It transforms the coordinates to another homotopy means topographical structure of both the coordinate system are going to be equal. So they transform it. And then another comes Lie symmetry analysis. So this is my research area somehow. So I use this approach to find out the solution of a PDE, of system of PDE. So there are three. power series has some drawback, like it has some error of convergence because you are writing in the terms of the infinite sum of the infinite series, so it might have some error. But this does not use any kind of summation. It just these two. It just transform from one space to another space, like x comma t will transform to a single variable xi, and xi can be like x over t to the power gamma, x to the power gamma over t, something like that. And then you fix one x and then plot over t. You fix another x and then plot over t. Like for all the value of x, you can write the solution, and then you are going to take the union of those solutions. So you will be writing the in n-dimensional hypersurface, but if you are in one space variable, then it is a surface because the solution is going to be two-dimensional. So the union of that, so those solution is going to form a surface in 3 dimension.
I'm very like interested in all of the Lie algebras and Lie groups and symmetries and all that stuff, but like applied to like non-commutative geometries and like in result non-commutative algebras, but like there's like I don't know if you have heard about like the Gelfand-Neymark theorem with C star algebra, and the Gelfand-Neymark theorem states that if you have a C star algebra, then that C star algebra is star is isomorphic to an algebra of operators in a bounded Hilbert space.
Yeah, so the same thing, the same idea has been follows in the symmetry analysis. But the thing is that I don't do a very theoretical analysis. I don't use the bounded operators in C star algebra to prove the Lie algebraic things, like a lot of theoretical things. I just use the transformation, and I say that.
Oh, you use like for Fourier transforms?
Which form?
Fourier transforms.
No, I don't use this form. I take like x star will be transformed to x plus t, xi t comma x comma u, and t star is like t plus, sorry, this is not t, this is epsilon, a small parameter like epsilon. Then for t, this is tau t comma x comma u. These are the infinite derivative function, and then u star as u plus epsilon capital U t comma x comma u. Now what I do, these functions are going to be only dependent on another variable xi, that is x over t. So I take this kind of transformation, and the transformation and the operation between epsilon, and if you replace some delta, like this parameter is going to form a group. So this kind of thing, but I don't explain very
okay,
because I am not a pure analysis student for sure, like a pure analysis mathematician. I cannot say that mathematician will be a big word for me. I am not a pure analysis researcher.
okay.
So bye. Because the way you were explaining me, I got it. I have read that, but it was going out of the head of Camilo. And I fondly He has been an engineer, like he has completed his study in mechanical engineer, isn't it? So that's why the theoretical I can understanding because when you are a physics student or you say that you are a mathematics student and when you are reading some topic of physics to use in your mathematics, so for a pure mathematician it is very difficult to use the physical things. In the same way, once physicist is using the mathematics, so it becomes little bit difficult. That is the way, because we are the human, we cannot cover all the topics, so don't worry. Yeah. Taylor series of x such that u of x comma t is equals to summation j varying from 0 to infinity z of z t x j uh, general uh, formal computation from ut is equals to uxx requires g not t should be g of t, because when we are going to take it at g equals to 0, so it will be like 0 g naught t x to the power 0, that is 1, that is free from x. So this is the first component that is free from x. So u 0 comma t, the first component will be the component u 0 comma t. So that because of that g naught t is going to be gt, z1 t is going to be 0, and j dash t is going to be j plus 2 z plus 1 j plus 2 z is varying from 0 1 2 dot dot dot. Therefore z2k t is equals to 1 over factorial 2k z to the power kt and g 2k plus 1 t is equals to 0, k equals to 0, comma 1, comma dot dot dot, which leads to u x comma t summation k varying from 0 to infinity g k t over factorial x over 2k, because the solution was written like this: u x comma t equals to summation j varying from 0 to g j t x to the power j, and we have replaced j to 2k, so it will be summation j, and now since this j has been replaced to 2k, so j equals to 2k, then g of 2k t x to the power 2k, and simply if we take 2k equals to j equals to 0, so it will be varying from k equals to 0 to infinity, and at the place of g 2kt we are using this, because for the odd term it is giving us 0, however for the even terms it is this function. Sure. Only indication, yeah. That's what I was explaining to, just because we took j equals to 2k here. So it will be summation 2k equals to 0 to infinity z 2k x to the power 2k. And this 2 is not going to matter, k equals to 0 to infinity, and we have the value of z 2k is this z to the power kt, and because of that x to the power 2k will be coming. Is it okay? Okay. Still you have doubt? Roberto? Okay. And if you want to check this, then you can expand it, you can take its derivative and can put it in this. Everything will be clear. I am not doing those things because this thing is like very basic. You can keep it back in the equations, in this equation, and then you can see. When as soon as you will keep in this equation, the first term z naught t is going to be zt because of the attribute of this, because of this. Now we are writing that extension of this equation. We then would like to choose a function g so that series defines the true solution of equation second. This was your equation number second. This was your equation number first. Equation second.
Factorial.
With gt be defined
Factorial.
by c of t is equals to e to the power minus t to the power minus alpha. T is going to be 0, greater than 0, 0, t is going to be less than or equals to 0, where alpha is greater than 0 is a constant. Then it is a
Factorial.
good exercise to show that I am going to ask you to do an exercise today so that you will be aware how it is coming, how we are getting an information, because I feel that this is more theoretical thing, more theorem. It is not using a step by step to write the solution. I think he just gets the function that we are going to take this function and with this construction we are going to have the infinite solution. That's it. This number theta is equals to theta of alpha is greater than 0 with g k t is less than or equals to factorial k theta e to the power minus t to the power minus alpha over 2 k equals to 0, 1, 2, comma dot dot t is greater than 0. And hence the function you define above is a honest solution of 2 that also satisfies u of x type of solution to the heat equation with 0 initial data, and it is not identically 0 as u of 0 comma t is gt for all. I'm going to ask you as your homework. This is whatever number you are choosing. This is your uxt. Now what you will do, you will take this form of gt, this form of gt, In fact, z to the power k is nothing but z. So you have to take this form of zt and then just keep in this one and prove that it is satisfying this equation. This is your homework. Please do that and then tomorrow we can talk about the maximum principle for the second order. Yeah. Mm-hmm. Yeah. Oh, sorry. Not 2t factorial, factorial 2k. No, not 2t factorial. Because if you are going to write it factorial 2t, then how you will be? Yeah, factorial 2k. Yeah, it is factorial 2k. Cannot you see that? So when you will, that's why I'm asking. This is a simple thing. You can write, you can simply explain it like z0 t over factorial 0 is 1, isn't it? And x to the power 0 is so g naught t is going to be z of t. You can choose g of t whatever you want. Like if you want to simplify it, then you can choose it t just for your simplification, and then plus z1t. Now the most important thing about the Tychonoff that he did not choose ZT anything. He said that if ZT is going to be of this form, he gave a form of ZT. That's why I say that it is a self-made solution. That's why it might be confusing to you. I am working on that and I am going to see how we can use it in another problem because this was really interesting. When we talk about the uniqueness of the partial differential equation, then we say that we don't have the facility to write the unique solution of the partial differential equation all the time, all the time. Sometimes it is. So he gave this kind of, now the first restriction was that you have to have the homogeneous heat equation. The second was the constant initial data or the variable initial data, whatever he is, furthermore he is changing it to the constant initial data. And then he said that if the initial function is a particular function of this form, for all alpha, it is going to satisfy the equation. So that was my, I haven't proved that. So this is your homework. Now you can see that, you guys can see that this gt, z1, g2 all are going to be same, or like it is going to be the derivative. So you have to find out the derivative, just keep it. And then the most important thing, when you will take its time derivative, then it is going to give you the, in the space derivative, it is not going to give you anything, like this will be independent. You have to take only the derivative of this function, isn't it? So this is your homework, and please do that and send it to me one copy if possible. If you find, then I will keep it. I think it would be easier for you. I just did not try it. You don't think so? It would be easier for you because you have solved a number of questions. Roberto, I will ask you. This time I was really very happy. There was a question, the question number second in your exam, and everyone has done it in a right way, but Roberto, he has explained it in a right way. Since the solution of the Laplacian equation is going to be a harmonic function, and then he is proceeding. It was really, I was expecting that explanation exact. Yeah. Because, yeah, so that was just a point. It means you guys are understanding the thing, how it is related. Because that I use a trick. Rather than writing it as a harmonic function, I say that, okay, so this is the Laplacian equation proof that the solution is going to be constant under this condition or something like that. Isn't it? If the solution is constant on the boundary, then it is going to be constant. I said something like that. So the main point was finding the fact that the solution of the Laplace equation is the harmonic function, because I proved it for the harmonic function. So this is the way how you are going to find the questions in your exam. Is it? So every time when you are reading something, I would strongly recommend focus on the small things, not on the big things. Small things. Okay, so we are going to meet tomorrow.